All right, guys. So midterm one. I have seen the exam, which is great. So I know what's going to be on there. Okay, so you're gonna have four questions. Number one, you're gonna have a resistor combination. Okay, you're gonna have a resistor combination. You are going to have a source transformation. Anything else? Oh, that's terrible. Better?
Yes.
Sweet. First transform, you're going to have a current divider. And you're going to have a main. Okay. I do that because people are going to file in and then ask the same question. So you're gonna have an hour and a half, really an hour and 20 minutes. You're gonna have four problems. What I say about Russell's exams are they are a time management exercise. A lot of people historically don't finish, and that's okay. If you don't finish, you are not alone in that. But whenever it comes to the exam, look through it, figure out what you're the most comfortable with, and start there. Don't start on the hardest one, start on what you know best, right? Let's go with one thing. Sorry. These are the exam questions, if you are wondering. So really just take your time, show as much work as you need to. If it's gonna be, if you are confident not writing I am 1, 2, 3, 4 every single time you write your matrix, you can write your I am matrix and just say I am, and I'll show that. But make sure you solve the problem, make sure you don't rush and get it wrong and all of that. But it is a time management thing. Also, what I was going to say is if y'all want to rent out calculators, I have calculators here for y'all to rent for the people who wanted to get practice with them. So I think I have 10. If you want to give me your ID, that way that we can actually all practice together whenever we're solving MAME and NAME. So if you don't have one, go ahead and now.
I'll have a Matt's ID, but I'll trade you my Costco card.
I'll take a Costco card, yeah. Okay, so 1, 2, 3, 4, 5.
Oh, how about you said ID like
You're fine. Okay.
we have to say that.
Yes.
That's all.
It should be.
Yeah.
Okay.
Some of the questions can be, like, absolutely, but I'm not sure what it is.
You found it? Well, bro, my dad has been to go. I texted him, I was like, hey, I'll get it to you on Inspire. Like, all right, it'll be there.
Can't remember.
It's like, okay. I bought it, like.
Can't.
They didn't great. I know my dad.
Also, if one of y'all wants to, is there like a rock or something we can crack that door open? I don't know. Well, I guess technically there's rocks everywhere in this room. but
Oh, yeah.
are they gonna get mad if I put a rock up? They probably have purpose.
They study walks for me.
Okay, sweet. Thanks. But you might need to. You might need it. Yes. So otherwise, what else do I got? Just yes. There we go. So it's open book, open notes. You can have your computer out to read the materials. Please do not go on the internet. A new one, even like it needs to be offline. You cannot watch videos though. You cannot download a video and watch that offline. That has been a new rule I've had to implement, I guess. And with that, no headphones, because people got nifty and tried to download my reviews and then were listening to it during the exam. It's not allowed. I can't have y'all doing that. And yeah, so you can have your computer out, you can have your notes. What I recommend is making yourself a cheat sheet. I recommend writing a piece of paper, front and back or something, put all of the equations down that you're going to need, right? Your current divider, right? Your voltage divider, anything. Just so you have a reference, so you don't have to be digging around.
So are we allowed to be online just to like Canvas to look at the materials? Or
So downloads. You got limited space on your computer?
No.
You just like print them out.
You can print them out. That's a lot of paper. I like pen and paper as well, but just having them as a backup is helpful. For electronics and circuits too, that's when the materials they're great because you have all of your constants. You have all of those equations that you don't want to write down. Yes. Hour and a half. Hour 20. 4 questions.
So there will be no name, right? Just name.
Correct. It's going to be a MAME question, not a name question.
No voltage divider question.
Correct. Yeah, so good that it's no name just because that was recently taught, but I like name better. Some people like MAME better. Very, very up to whoever it is. But I'm trying to think if there's anything else I have about general test taking strategies before I get into it. Do y'all have any other questions about before we get into problems? Sweet. Cool. We're gonna start in that case. I have a couple printed out stuff to do. So this is first question. Okay. Oh, that's important. Read the question. Read the whole question. I get people like that on problem sets. It happens on exams. Make sure you know what it's asking for. Don't just assume it's a MAME question and solve MAME. It might be asking for something else. Okay, so
Will you be uploading?
yes, so it's being recorded on Teams right now. And I'm going to send out the Teams link. And it's on the HKN Teams. And there are some old reviews in there as well, if you want to go watch it. And I think I just got Grady to upload them to the HKN YouTube as well. When this one will be uploaded to YouTube, I'm not sure, but it will be on the Teams recordings. So I'll send that link out right after this. Cool. Let's go ahead and read. The network NCD shown in figure 1A contains a collection of resistors in series and parallel connections. The network is to be connected to terminals AB with resistor RX in series as shown as figure 1B or in parallel as shown in figure 1C. Using the resistor values as shown, you are asked to do the following. determine the proper connection and calculate the value of Rx that will set RAB equal to 3K and repeat for 5K. Not too bad. So we'll start with, we'll just start reducing it down. Something that I have had people ask is these diagonal guys, right? Those are weird. So all that this means, whenever we have a node here, and I forgot to bring a highlighter, and I really meant to bring a highlighter, but
Is that a highlighter?
it's a very thick highlighter. Might use it.
I think it's 12, like 8.
Oh yeah, so this is the percentage, and so it's a total of 25% of the exam. Total of 25. Part A is worth 13 of it. Part B is worth 12 of it. So whenever we see this, whenever we have a node, we can split that up, right? Because whenever you just have a wire, it's still part of the same node, right? So if you have this is all the same node, right? Okay, so what we can do here is we can take this and kind of shove it over so that these are straight. So we can take this and I'll go ahead and draw it out. My resistors are not going to be pretty. I apologize in advance for that. So what we can do here is instead of having this be diagonal, we can take this and push it over. So now we have a straight one. And then this is still one node, but it's a wire instead of just being a point. And so this is this. And so we have R8, R11, this is R9. And then we come here, we still have another here. So this is R10. And then we have R7 here. And then these two are connected at this same node, right? So does everybody agree that that is the same as what's right there? And so, so this node became this wire, and then this node up here became this wire. Okay, so I'm gonna keep drawing it. So then we have another resistor here, we have R4. No, that's not true. Ah, this is horrid. I'm so sorry. R4. I want to redraw this. I am angry. Okay. I didn't leave enough room for this, but this is kind of the proof of the diagonal stuff, right? You look like you have a question.
Are you gonna give us scratch paper?
Yes.
Are we going to need to show the reductions like we did during homework?
So
Like the step-by-step reductions of, or do you
Excellent
only care
question.
about the answer?
I care that you show me enough to tell me that you did the work and you didn't just copy down the answer.
That we understand.
Yeah.
Okay.
What we can do now is we can just do the math. I do not need you to write and simplify it down. Okay. Every single time I just need you to show me whether it's with circles or whatever that you know how to reduce it. So let's go ahead and start over here, right? Let's just start reducing it. R8 and R11, those are in series, right? Also, I've said this in my office hours before, but if you see terminals, if you see this terminal over here, you're going to want to start on the other end. Because if you have something in parallel with these terminals, that means it's in parallel with everything else. You're never going to be able to reduce this until you reduce everything else. So don't start by the terminal, start other places. Like on, I think one of them, and on your homework question, like on this, if this was the other way around, you might have to start reducing this first, but it's in order to reduce the opposite side. Right? So it doesn't mean that you always are going to start from the opposite like point, but start over there and then work your way over, right? Cool. So let's do R8. Let's start with R8 plus R11, right? What's that equal? Can y'all see it? Okay. Okay. And then what's next?
Number 6 plus 1 over R9 to the negative 1.
So then it's going to be this. So it's going to be 6K in parallel with R9, which is equal to, if someone could do that in the calculator, because I can't do that in my head.
If we call it REQ, say REQ parallel RQ.
Yes.
There's gonna be a lot of REQ.
I like that. Like,
It's a little bit. It's going to be a little bit a lot. I like arrows. So if you wanted to like, you did 6K and then did an arrow to REQ, that's helpful. And for the resistor combinations, I totally get if you want to just not show any work and just do it all. But if you make an error somewhere and I can't follow your work, I can't give you credit. So show enough so that, like I said, I see that you did the wrong. But if you feel like you need to redraw it every time, please do. If that will help you and that is how you need to solve the problem, draw it out, take your time. If you do not need to do that, don't do that. So 6K parallel with R9, 12K, 4K?
Yeah.
4K, beautiful. And then what's that gonna be?
I mean, excuse me, series of 10.
So it's gonna be 4K plus. Then which is what, 6K? So now let's go ahead and I'm going to redraw this just for the review sake, right? So we condensed this down and we just got to R10. I'm trying to decide how much I want to redraw this or not. Possibly. We don't anyway. Better?
Yes, thank you.
Yeah, of course. So let's go ahead and we'll do this drawing, right? So we have our R1. Seven, and then we just did this. This is 2K. That's 4K. So now we can kind of see better, I hope. This is our 7. 7. Etc. So what's the next step? I don't want to spend.
You asked for 15.
We did that and then
Parallel crossing.
perfect. So it's going to be 6 in parallel with 30. What's that going to equal?
Okay.
Okay, and then what's the next step?
Series with R6.
R6.
Just parallel crossing.
Plus 10K to 15K, right? And it's 15 in parallel with 3. Am I going too fast? Okay. What's that equal?
Okay.
Okay.
Series with R4.
And I'll go ahead and redraw this again. So we just got to R5. So this 2.5 goes here. So we can see better that this is in series, right? And then that's going to be in parallel with 15, right? Perfect. I like colors if you can't tell. 10 in parallel with 15, 6, and then it's going to be 6 in series of 6, 6, 12, and now it's in parallel with 6. Is that equal to 6? No. 4K. Okay, so now let's, equivalent is 4. Let's come back to the question. What was it asking in the first place? Was it asking for that?
No.
What values are?
Party.
So this is 4K. If we're trying to get to a smaller value, is it going to need to be in series or parallel? Because parallel is always going to be smaller than the original. So because it needs to get to 3K, it needs to be in parallel. So we need a parallel. So we need, I'm just going to go ahead and write out, let's see that right, yeah, the equation. So it's going to be 3K needs to be equal to 4K parallel with X. And this is where your calculator can just solve it, right? So I'll go ahead and show you how to use the solve function. Okay, so this is going to be how to solve for a variable, right? Just in general. You're going to go to menu. This is our big repository of all of the things. We're going to go to algebra, and you can either go down or you can just hit the number 3. Short little things and solve. So it's just going to say solve. And if you can't remember where it was and you know what the word is, you can just type solve. So what we're going to do is we're going to say 3K. I'll do 3,000. I tend to do the E. Then we're going to have this equal sign. So it's equal to and this is how I would do it. 1 over 4e3 plus 1 over x. And then after we write the equation, we're going to do comma all the way down here, the variable that we want to solve for. So I did a couple things in here. This 4e3 is how I get away with not typing a bunch of zeros. I find that faster. I have said this before, but I'm lazy and I like pushing the least amount of buttons that I have to. And then come again? Oh yeah. So on the division, yeah. So calculator functions, this control button is going to give you what all of the blue functions are. So if you control division, you get a fraction. Yep. And then comma x at the end, and it's going to give the x is equal to 12,000. Mm-hmm.
Yeah, I did it like 1 over 4 plus 1 over x to the negative 1.
Mhm.
It still gave me the right answer, but it was something caution.
It gave me the caution symbol too. Whenever you have a bunch of fractions, if you have like negative numbers, it can get into domain errors. If you start dealing with imaginary stuff, the domain might be larger than the domain of the input. That's all that means. Don't worry about it. Yes, so you're gonna go to menu and then algebra, because it's an algebra equation, right? And then solve. And again, if you want, you can just do menu 3, 1. You want to get quick with it. Obviously, if you wanted to do it the long way, you can do it the long system of equations way. You multiply it out, but this is faster if you can know how to use it, obviously. Now we can prove that this is right. If you were curious. 3,000. So what's the second part?
Find range.
Series.
Mm-hmm. So repeat for 5K. 5K bigger or smaller than 4K? So it's going to be in
Series.
perfect. B. Theory. And this one's easier. What's it going to equal? Perfect. Not too bad. What?
Is there a word clear on?
Yes. So if you do control delete, it's clear. Yes. I'll get into more like calculator helpful tips later. But what you can also do on that same note is if you go up and then hit enter, it'll give you the same equation you just typed in. And then, like you said, clear. But if you wanted to come up to this solve and change this to like 9,000, you could just change it like that. You can do it fast. So this box is weird, right? It's how do we feel about this box?
It's just saying that it's like it's enclosed and we can't see inside of it, right?
Mm-hmm. Exactly. So the reason that he does this box is so he can do this. All the box means is that there is an equivalent resistance in it. And so it's a way for him to write this easier. But if, and this is the moment of hint, hint, wink, wink, right? If, say, there were to be 2 of the boxes, there would be 2 of these equivalences. And then he has connections coming out here, but then he could like do something weird. Yeah.
So how do
Yes, good night, gang. You guys, good night, gang.
Okay, so backtrack. If he wanted, he could have two of these boxes. But then down here, what he could do is he could label this box A, and then he could have another box called box B. What he could do is then he could say something like this. This is so
we just solve A first, we solve B.
So all this would mean is that you would solve A first and then say you had another one of this, right? So you would get the A is equal to 4K. All you'd do here is you'd come in this A, you'd say it's 4K. It's found B, B is equal to 6K. So what's the equivalence from 1 to 2?
Thank you.
Perfect. So we see that this is going to be them in series. So maybe, hypothetically, he might do something where they might not be in series. Something like that.
Yeah, how would they work in parallel, it would just be behind.
See, I can't quite give you there. I can say think about it. I can't quite give you the what the test is going to look like, okay? Maybe. It might be series or parallel. It might be parallel and then series. It might be something funky like that. Who knows?
But if it's, okay, so it's just parallel, they would just put it like parallel to each other and then we just figure that out. So really they can just substitute that for another resistor.
But yeah, it'll look scarier. This looks scarier than it is. Boxes look scarier than they are, but they're not bad. Okay, so
What was the answer to part B?
1K.
There's only two parts.
Got negative 220,000.
Yes, so that is because can't really have a negative resistance, right? We were trying to figure out if it was going to be in series or parallel. So since we found 4K, but we need it to be 5K, what we're going to do is we're going to put it in series so that we can make it a bigger number, right? If the total resistance needs to be bigger than what we have,
Yeah, that makes
you are good.
you busy putting stuff in this calculator.
Yep. All good. Calculator, math, simple errors. So much of what I see. Okay, what do we want to do next? Do we want to do a source transformation, current division, or MAME?
There's
Source.
gonna be like a lot of I shift and shit.
No,
No, that's what I mean.
no I shift, no E shift.
Yeah, dude, that's not even talking about. He said, eh?
What is what?
I get it, you don't get it. Dude, I know, so.
Okay, let's do source transformation. Let's read the question. You cannot see it. Setup is rough in this classroom. Not like my hip keeps bumping into this. It's not comfortable. So the network shown in figure 3 consists of a collection of resistors, batteries, and current sources. This is going to be connected to a load resistor, terminals A, B. Calculate the value of RL that will produce a load current of 5/3 amps. Use operations of source transformation, source combination, and resistor combination to reduce the network to the equivalent. So there's resistors in this problem, right? That means that we're not going to use source dominance. We see resistors, source dominance is 90% of the time not gonna apply. So there's that. Whenever we come to our source transformation, we're going to use the God equation, right? What's our governing equation? V equals IR. Ohm's law. That we will remember until the day we die. That I still write on every single paper that I write. Just to look at, right? All source transformation is using that equation. If you're looking for voltage, you're going to have a current times a resistor. If you're looking for current, you're going to have a voltage divided by resistance. That's all source transformations are. And the resistor will never change. Right? So how do we add sources in parallel?
We can do it like, you want to make the current source,
Mhm.
try to make it parallel with the J1, so that we can subtract it.
Exactly. If we see a bunch of things in parallel, we should think, okay, how can I make these into current sources? And then if we see that things are in series, how can I make them into voltage sources? So first, we're going to take this. And what's that current source going to be? 12. What?
It's gonna be 10.
Right, then they
Yeah, divide.
10,
30.
Okay, now which way is it going to be facing? Perfect. That is because this positive, where the positive is where the arrow is going to point. The plus and minus of a current source, minus is at the bottom, the tail, and the plus is at the tip. Yep, that's what they're called. So we have 10 amps. No, 10 milliamps. 10 milliamps. And then this is 3K. Now this is all in parallel with this. So what's our total current going to be?
8.
Going up. Perfect. I'm just gonna do it in steps. I'm not gonna redraw the whole circuit every time. And y'all can do this as well. And also on that same note, if you want to just circle this and say current. Okay. And then add in parallel.
So they come together before they connect to the
What do you mean they come together?
like. So we have parallel, but then the C to D node, like, are connected back together.
So
But he's saying it's not directly as the data before. Building.
oh, okay, I see. So because this is just a wire again, we can just bump that up. We can just move that wire up. And so that is the exact same as this.
It just made me feel like.
Yes, without the wire, they are in series, but with it connected to other stuff, we got to remember that that's in parallel. So, and with that, this whole thing here is C. And this whole thing down here is D. And that stays. So we'll come down here and then what is the equivalent resistance going to be? Beautiful. Mm-hmm. And then what we have this. So we can see exactly. That looks terrible. But we see that these three things are kind of in series, right? We can see that. This is in series. So we're gonna think, let's change everything to a voltage source so we can add the voltages in series. So let's go ahead and do that. What's this gonna equal? Perfect. And then what about this one? Mhm. Pointing up, right? The first one. $16. This guy. And then what about this down here? Which way is it pointing?
Humans. Or, yeah.
Yep, perfect. $16, we got $34, we got $66. Now, we have plus here, and plus here. Are these all in the same direction?
Yeah.
Nope. So that sounds right. Do we agree with that? We got 34 plus 16 is 50 minus 66. And then 4K. And then a reminder here. We see this is in parallel with these terminals, right? If there is stuff connected here and here, this will never be in series with the rest of it. So if this was a voltage source here, that's a better one, they would not be in series. So just remember, if there is stuff connected over here, can't add it in series, it's in parallel with that. So now what do we got? We got 16 here, we got 4K, and we got 10 milliamps. What are we gonna do now? Perfect. What's it gonna equal?
Four, yeah.
So 4 going down. Let's
Oh, excuse me.
okay. So then we good to go ahead and combine the two sources. We got 4. Oh, right. Mm-hmm. Sorry, the resistor value came from here. We had 2K here, 2K here, and then we had another 2K. And so 2K, 2K, 4K.
Going back to what you said, if
Yes.
on the far right, that current source was a voltage source,
Mm-hmm.
we couldn't have control.
Correct. Correct. Because definition of series is that two things are directly connected and connected to nothing else. So if there is a resistor, these are in series because this node, they only share with each other. If there's anything else at that node, they are no longer in series. So we got 6 milliamps, 4K, and now we need to figure out this RL. There are two ways to do this. What do we see first? How can we figure out what the current's going to be? So we can do that. the other thing that we could also do is we could do a current division. But
Easiest thing.
It'd be 6/6/1/4. Over.
yes. So, but we can go ahead and change it to a voltage source first. Let's do, because that's what people immediately think of. 6 times 4, was that 24 volts going up? So we need 5/3 amp going through it, right? Right? So current is going to equal to voltage over resistance. So we want 5/3 is equal to 24 over 4K plus RL. Now, we can just plug that in the calculator. I mean, it's not that entirely hard to do the algebra, but let's go ahead and do another example with the solve, just so we remember, right? Menu, algebra, solve. So we have 5/3 equal to 24 over 4K plus X, comma, X.
I thought that resistor was still in student,
It is.
or I mean, parallel.
No. That's
Because we have stuff.
not right.
It goes down, but it's very.
So that's funky. So that's negative.
Yeah.
Huh. There's a typo here.
Volts divided by ohms, amps.
So there's a typo here. I remember this now. I had this on my midterm when I was in circuits 1. So we had 6 milliamps, right? Is there any possible way that we can get 5/3 amps? That is bigger. If we have a current division, we're never going to have a bigger current than we started with. Right?
So, what we.
So the question is supposed to say 5/3 milliamps. That is what the question is supposed to say. However, there is a typo. So if there is a typo, what's 5/3? So it's 10.4 milliamps.
That's a third K, just leave it. So it's like using K on 10 milliamps. So like.
Say that again.
Instead of just like answering all the zeros, just put it in like, understand that you're using K ohms and milliamps.
That should.
Yes, you can. However, be very, very careful at the end to know what unit you're in. Because if you just say 10 amps and it's 10 milliamps, I can't give you credit. So you can, but be careful, basically. So 5/3. Hold on, sorry. That's still the thing. Nope, because I'm stupid. There we go. Okay, so if it was 5/3 milliamps, right? It would be 1.1666 3. Are we tracking? Okay, so it's supposed to be this. It's supposed to be 10,371.3 ohms. But with the typo, it gives negative resistance. We did it right. There was just a typo. So what we are going to ask and what Russell will do, if there is a typo, solve it the way that the typo is. This is the way we ask the problem. You can tell us this gives negative resistance. This is not possible. So that's impossible. However,
5/3 milliampere, right?
Hmm?
Should be 5/3
Yes.
milliampere.
it should be milliamps.
But why is not nothing with 5/3 ampere?
Come again?
If it's 5/3 ampere, then why is it typo?
Okay, so current division, right? Let's come, instead of doing this way, let's do current division. What is the current dividing equation?
You want the budget.
So the current that you're looking for, right? Times the total current. And then there's two ways to write it. The way that I prefer is 1 over the resistor that you're looking for divided by 1 over Rx plus 1 over Ry dot dot dot. You can also write that this is Gx, Gy, Gz, and I say X is the one that we're looking for. The other way you can do this is all G is 1 over R, right? So is this value going to be more than 1? A fraction, like part of something divided by the whole thing. It's never going to be more than 1. So is the current ever going to be more than the total current? No. So we have here 6 milliamps. 6 milliamps, and we are trying to get 5/3 amp, which is equal to 1.66 amps. Which is bigger, 6 milliamps or 1.6 amps? That's not possible. So that's why it's a typo. That is never going to happen. So yeah, unfortunate that I picked a problem that had a typo in it. That's my fault. Oh, wow. This is even from my semester. I even printed this from, wow, yeah.
I think we have the same exact problem, but I think it was just a different like games.
It was. That's funny. Good job, Grace. But how do we feel about source transformations? Sweet. All you got, just remember V equals IR, and resistance never changes. The right answer, if there wasn't a typo, is this. Yes.
It's like a big announcement. You said like 10.4K, or did that mean 10?
Oh, please say K. That makes my life easier. And this is a good one. So this isn't my calculator. This is one of the IEEE calculators. So under document settings, there's a lot of stuff that's going to be more important with EMAG, but this calculation mode is interesting. You can either have an auto, exact, or approximate. If you do exact, it's going to give you everything in fractions. If you do approximate, it's going to give you everything in decimals. And here, I'll actually show you an instance of this. Whenever I typed in 5/3, it gave me 5/3, which is the exact answer. If you want the decimal answer, you can do Control Enter, which is these little squiggly guys, right? And so that's going to give you the approximate answer. And so if it gives you some weird fractions, that's how you get the decimal. And if you ever wanted to change it so that you always got one of those, that's how you would do it. And then, not that. Nope. Nope. Exponential format. I always keep this in engineering because that is the best thing ever. Do y'all know what engineering notation is? It's the multiples of 3. And so instead of this, it should give me 10K. And so instead of having to figure out what the thing is for K, because scientific notation is a little rough. If you keep it in engineering notation, you could say K, mega. It's especially helpful in electronics because then you get pico, nano, all of that stuff. So tips and tricks for the calculator. So let's do current division quickly. How are we doing on time? Okay. We'll do. I don't want to do this problem. We're going to do a simpler problem. I changed my mind. So let's just come back and let's practice using the equation, right? Let's just do conceptual based equation.
I do have a quick question.
Yeah.
In regard to.
Yeah.
That's I total times 1/r. I mean, it's basically just a resistive network, right?
Mhm.
Why is that not voltage?
Because it is not the true voltage, it's the fraction, it's a ratio of the voltage. So you're doing a proportion thing. So and the way I explain it with voltage division is voltage is directly proportional to resistance, right? When resistance goes up, current voltage goes up. Current and resistance are inversely proportional. So whenever there is more resistance, there's less current if this stays the same. So
Isn't that technically like Siemens?
you could say it's in Siemens, yeah. You could say it's conductance here. That's why we have an option of doing G.
I guess really it's a current. If it's in Siemens, then it's current divided by.
If you take the
R
SI
would
unit,
be-
everything would cancel, just I is equal to I. That's why it's in.
Yes, exactly. So it's a ratio. You're doing a ratio of resistance to resistance. And whenever you divide resistance by resistance or conductance by conductance, the unit goes away. So it's just like you're saying,
Essentially just turns into a scalar.
exactly. So you're doing the ratio of, say, this Rx, let's just do like a really simple. This is 4 and this is 2 ohms. So, and we are looking for this. So we're looking for this current. So this would be 1/4 divided by 1/4 plus 1/2. So gross, what's that equal to? So that's 1/3. So all that this is saying is that the current going through exactly 1/3 of the total current is going through this resistor. This is also cool, and you can teach current divider this way if you, and this is a very big if you only have 2 resistors. If and only if you have 2 resistors, Ix, so this is going to be Rx, this is Ry. Ix is equal to I total times Ry over Rx plus Ry. So if there's 2, then you know that it's going to be opposite here. So that means here is going to be 2/3, right? That is because this is 2/3 of 6, right? That's, of course it is, but it's a proportion. I feel like I'm rambling, but does that make sense? Sweet. That's kind of conceptual. If we have, what if we added a resistor here? So I'll redraw it again. But why do we need to combine the parallels first? So we don't actually know what this current dividing we don't know what the resistance total is. We know do you have to do that?
What? Resistance and everything. I don't know.
Yeah, exactly. So what we do here is we are going to combine this and find, no, the current's the same. That's, you have to do that for voltage divide. Yeah, if you were trying to find the voltage here, you'd have to do that. You'd have to, so if this was a voltage source here, you would have to combine them and then figure out what the voltage just across this one would be. But the current's actually going to be the same in this one. So, and we can show that. Yeah. Do we want to do that? Do we want to spend more time on current divider, or do we feel like current divider is not bad? Does anybody want to stay on current divider? It's totally okay if we do. Don't be scared.
How about we do an actual current divider problem?
Yeah.
This one is really long.
Yeah, no problem.
Is the test gonna be that long though?
The one on the test is not going to be this long. That's why I said we weren't going to do this.
Well, think about it. Before the test, you want to do the hardest thing possible. So the test is like, oh man, this is.
Is there some time?
I mean, yes, we can. I was gonna just go to MAME. I was gonna go to MAME and spend more time on MAME,
Get paid.
and then,
Did you maybe come back?
yeah, that's what I was gonna do. Okay, cool. This one, MAME problem, not terrible. Not bad. It's 4 meshes. Mhm. Mhm. Let's break it.
Oh, doing math in my head.
Oh.
So whenever we see MAME, the mesh analysis matrix equation, we're going to think of three things. We're going to think of mesh currents. We're going to think of voltage sources. And we're going to think of resistance. So this means we're going to put all of our dependent equations in terms of our mesh currents. All of the sources in the problem need to be turned into voltage sources, and our matrix and resistors needs to be in terms of resistance, not conductance. It's the other. For name, this is the exact opposite.
If you're gonna have us like, maybe I'm just gonna throw a out, like put Siemens in a mesh problem.
He might put resistance in a name problem and you have to convert it to Siemens. That's not out of the ordinary. Sometimes he does it for you, which is convenient for us, but not always the case. I've never seen him put Siemens on a MAME. I don't think he'd ever do that. So let y'all finish it up. But there's two ways that we can start. We can either start with our passive matrix and write the original equation, or we can write our equations for our dependent. Okay. I dig it. So for meshes, we're gonna have a 4x4, right? So I'm gonna do my whole thing. So who here, and this is more of a math. How many of y'all before like looking at these problems and still now have not learned matrices and matrices operations, like matrix multiplication?
No, it's a little bad. So.
Yes. Yes. Yes.
Never trust you.
Yeah.
The class was supposed to be, they had a really good intent with creating class. The professor has not pulled it off.
Oh, 2023 award.
Yes.
Yeah.
Is that the EE?
Yes.
Oh, yeah, I avoided that class.
Yes. Great intent, could have been a great class, but it's not right now. So I will go over, that's why I'm writing this the way I'm writing it. So simmer down, please. Whenever we write matrices, typically you write n, and then you write, first you say the row and then you say the column. I'm gonna start from basics. I'm gonna start from basics, okay? If you know exactly what I'm talking about, then this part isn't for you. Okay, so whenever we label matrix, we say n. Can y'all see that? Kind of. We say that this is n, and then we say the row and then the column. And so this is n11. This is going to be n12 because it's the first row, second column. This is n22. This is n33. This is n44. And 1, 3, and then same over here, and 2, 1, and 3, 1, and 4, etc. Can y'all see that enough? You get the gist. So this is how we label it. And I'll go ahead and write this out for So all of these are the diagonal, right? The ones that are the same row and the same column. Right? So if this is the second row, second column, that is a diagonal. This makes nice, pretty diagonal, right? So when Russell says all of the diagonal elements are going to be positive, it means that these four will be positive numbers, and everything that isn't those, so all of these guys are going to be, I didn't make this big enough, negative. Everything else here. Want me to redraw it? That's too small. I apologize. But do you want me to redraw this, or do you get the gist of all of them are negative? Sweet. Cool. So now how this translates to name and main. So this is more for explanation purposes that I write these 1, 2, 3, 4. The rows, these rows correspond to loop 1, loop 2, loop 3, and loop 4. So I'm writing these. I write the ones on the top for the resistive matrix because this is going to be what's shared between all of these and the corresponding first, second, third, and fourth loops. So the diagonal elements are going to be the sum of all of the resistors in that loop. Just easy. Just sum every single resistor, and for name, sum every resistor that is connected to it. So if there's a branch connected to the node, every single resistor that's connected. Name isn't on the exam, just for reference. So
Next one.
yes. It'll be either on the next one or the final in some way. You're gonna be tested on it. So the diagonals are that, and then all of the off diagonals are the resistance that's shared between the row and the column. So it's what's shared between loop 1 and loop 2, loop 1 and loop 3, right? So let's go ahead and write this out. What are all of the resistors in loop 1? Got 2, 3, 5, right? So it's going to be a positive 5. What is shared between 1 and 2? Negative 1. Perfect. Now what's shared between 2 and 1? Yes, back there.
It's, if one mesh loop shares more than one resistor with the other, you just happen to.
Yeah. So now what about 1 and 3?
Is there a reason why it's negative?
Yes, mathematically.
Like, you know.
Yes. Do you want me
Well,
to like do the proof right now?
oh, no, I'm just saying.
Well, it's like it's a proof. This whole thing is derived from KCL and KVL. It's derived whenever there's the voltage through this resistor, right, is going to be the sum of, where's my pencil? It's going to be the sum of mesh 1 and mesh 2 going through this resistor. Whenever we're looking at the first loop, if we have them all clockwise, then that means that it's always going to be the loop that we're looking at minus the other loop. And so there's a big mathematic proof, but that's why it's going to be negative, is because it shares both currents. And then it's the same way for loop 3 and 2. Whenever we're looking at loop 3, that's going to be the positive current, and then IM1 would be the negative one. Cool. So what's shared between 1 and 4? Nothing. Yay. Okay, what about everything in loop 2? 9. 2 and 3. 2 and 4, -1. Y'all good with me doing the across and then straight down, right? Exact same, perfect. 3, 8, 3 and 4, -2. What about 4? 6, beautiful. Now this is gonna be multiplied by, I am 1, I am 2, 3, I am 4. And that's another way to say, to see, look, this is loop 1, loop 2, loop 7. This is going to all be equal to the sum of our voltage rises. That means that if it is a rise, it is positive. Typically, a drop is positive, right? That is still true. The only reason that it is positive voltage rises is because of this equal sign. Hypothetically, we would still be adding all of the voltage drops being positive. But if we move it to the other side of the equation, all of a sudden now, all of the voltage rises are positive, even though they were negative on the other side, right? And so voltage drop, still always true, but for this matrix, we're looking for positive voltage rises. So let's look around, and a positive voltage rise means it goes in the negative or positive? Negative terminal. Perfect. So what do we got in mesh 1?
Or my second bias.
Yeah. RMI7 minus, do we want to do EG or 2? I like numbers. So that's the first loop. What do we got in the second loop? Yes. Correct. Let's stay RMI7 just for this first step. Okay. Oh, no. If you want to immediately go to plugging in numbers, that's fine. If you want to do everything symbolically, that's fine. That is pure preference. Loop 3, what do we got? And then 4. So this is our first step. Great. So now what we need to do, exactly, because algebra, and I know people who, you've been to my office hours, you've heard this a million times already, but this is an algebra equation. These are our variables. This is our x. We want to put everything that has an x in it to the left side of the equation, and we want all of our numbers on the right side of the equation, right? So we want to separate our pretty nice numbers, which is -2, 0, from our dependent stuff. So let's go ahead now and write out our equations for I7 and V2. So I think the easier one is going to be I7. We are looking for current, and we're going to write it in terms of current, right? We need to make sure that what we're writing it in terms of and what we are looking for, the units match. So we're going to write this in terms of current. Do we need to do anything different to it? So what is our I7 going to be in terms of our mesh currents? Sweet. Why is it IM3 minus IM4? So the arrow is pointing in the same direction as I7, and that means it's positive. That means that it would be the bigger one, right? So it's IM3 Yeah, and then this guy is coming up, he's going the opposite direction, so he's subtracted. And we have current, and we have current, and so everything's happy. V2. What is our equation for V2 gonna be? V2 minus IM1, perfect, times R2. So we need, we're looking for voltage, we need to know it's gonna be current times resistance. So it's gonna be 1 ohm times the current, which, like everyone has said, is IM2, because we are looking for a positive voltage drop. Whenever we rewrite the equations, we are switching our brains over momentarily to that voltage drop is positive. And so for this, if it is going in the positive terminal, it's positive drop. And so IM2 is the bigger one. IM2 minus IM1. So now all we're going to do is we're going to plug this in. So RM is 4, mu is 2. So I'm going to intermediate step of 4 times IM3 minus IM4. Negative 4 times IM3. 0 and 2 times IM2 minus IM. Yeah. Can you see that at all? Sort of. Sorry. So now, like I said, we want to get our variables over to the other side of the equation. To be able to subtract these, we have to make this look the exact same as this. So we need it to be a 4x4 matrix times our x, which is our IM. And so the way that we're going to do that is, I'm going to go to the next piece of paper so I can write it there. All these things that are, everything's in the way. Yes.
I just had IM2 minus IM.
Yes. So remember, we're looking here for a positive voltage drop because we are just looking for the voltage. We are saying that voltage 2, the voltage drop over R2. And so because it's voltage drop, IM2 is what would produce a voltage drop. Because our passive sign convention, right? If it goes in if man, I'm doing great. There will always be a voltage drop over a passive element, right? A resistor will always have a voltage drop.
So you express the voltage drop, right?
Mhm. So whenever a current goes into a resistor, it's going to be a voltage drop. And whenever a voltage drop is, the current goes in the positive and out the negative. So we see that IM2 goes in the positive, out the negative, and so that's positive. The other way, IM1 has its positive here and negative here. And that's the opposite.
Because IM1's going. Yes, yeah.
Yes. And so that's why it's subtracted.
I dropped arrows on all that.
Yeah, that is.
The arrows go against each other, it's negative.
Mm-hmm. Very, very true. Very much so. You can write your plus and minus on all of them if that helps as well. Said, right, all of the work that will help you get it right. So we're going to come back over here now. And we're going to do another I'm going to show another thing about matrices. Matrix multiplication defines, we have IM1, IM2, IM3, IM4. Whenever these two things are multiplied, it comes so that IM1 becomes this row. So this comes to the column, not row, column. IM2 comes to this column. IM3 comes to this column. IM4 is in this column. You can't even read that. 4. So what we're looking for is we know that this is our loop 1. So we're looking for, in our first equation, how many IM 1, 2, 3s, and 4s do we have? And whatever that amount, whatever that coefficient is what we're going to write in our matrix. Okay, so in our first loop, do we have any IM1s? Perfect. We have 0, IM2, 0, IM3, IM4, -4. Perfect. Next one. Perfect. Just make sure you multiply that negative out. Next one. All zeros. Love zeros. And I don't like giving zeros though. Last row. Yeah, sorry. -2, 2, 0. Perfect. Now what we're going to do is we're going to take this matrix and we're going to move it to the other side of the equation. So we are going to subtract this from this. And the way that I would like you to denote that is to write a big friendly arrow that says subtract. So that I know that you did the right thing and you didn't just make a math error somewhere, right? So I'm going to write this over here. So we got 5. Let's just go ahead and list row what the values are going to be, okay? So we got, you can see that, right? Sort of, right? So list out 5, right? Then 1, -6, and 4. Yep. So remember, it's going to be 0 minus -4. 4. So we got -1, 9, 0, -5. Perfect. Next. Beautiful. And that's what I mean. You can just write that. That's going to equal to -2, 0, 2, 0, right? So from here, all you do is put it in the calculator. So one way to do it is to multiply the inverse of this times this, right? And that's how Russell says it in class. So this is our so it's and matrices are dependent where they are. So it's not EM times the inverse of RM, it's the inverse of RM times EM. The other way, the way that I like to do it, is something called a row reduced echelon form, which
With the R&D.
RREF, which
5R1 plus.
is I could hopefully at some point you'll learn it in linear algebra what it means, but it simplifies it down so that they're right. I'm just saying it'll do like a 1, 1, 1, 1, and then give you your values. So
Like X is only in that.
the way that you do that, so you put RM here and you make it a 4 by 5.
Yeah, well,
So you make it a 4 row, 5 column. And you're going to put your EMI here. So I'll show you how to do both ways on your calculator. So this guy here is how I get my matrices. It's a bunch of helpful things, right? So we do this one, and it'll ask us how many rows and how many columns. So we want, do y'all want me to show you the inverse way or just the RREF way?
Just the R, yeah.
Sweet. I like that. So to do number, you do number and then tab to get to 5. Tab, enter. Right? So then for the first 4 columns, we're going to do just what we got our matrix here. And then in the last column is what we're going to do our,
These values there.
yes, exactly. So I also totally forgot. To get to the REF, you go menu. We're going to go down to our matrix and vector, and then reduced row echelon form.
Enter.
Yes. You can either do that, or you can literally just say RREF, which is faster. And then just make sure that you have a parentheses there. So make sure you say REF and then have a parentheses. And then
Biggest matrix.
we've done a 5 by 5. I don't think we've done bigger than a 5 by 5. So then to get to the next thing, just tab, and then we can get all of our things in pretty quick, right?
No, I'm 10 minutes. It's lots of this. I want to see. Like, if you have already. So we begin from the two, which you I forgot to do.
Gross. Fractions, not fractions.
Yeah.
So is that what y'all got?
Yeah. Definitely.
that chip was awesome. You only give us a 5 by 5. I'm just.
Okay. I'm pretty sure that this is in fact correct. How do you feel about matrices in the calculator? Do you want me to go over that again?
I would.
Yes.
Right, I'm gonna need to just do it a correct spot.
What did we get? Do we see any issues?
So you just, multiply RM versus the, EMI, right? It wasn't what we did before, so like with the current, one, we're adding that one matrix with the 0, 0, 4, minus 4.
So we subtracted that. So what we did with we subtracted this from this, and we got this, right? So we went like -2 minus 4 equal to -6. And so this is technically, you want to write this the way that Russell does it, RMP minus RMD. And then we took this and we put it in this augmented matrix. So we made it 4 by 5, 4 row, 5 column. The other way to do this, and I can try to do it pretty quick, is to do the 4 by 4 and then -1 times your 4 by 1. Then what was it? -2, 0, 0, 0. And it'll give the exact same thing. So either way works. People who got something different, what did you get?
Maybe they want. Something.
Same thing. Same thing? Sweet. Okay. So that's matrices in the calculator. Do we want any more help with the matrices in the calculator? Sweet. For that weird problem, all you would have had to do on your homework is just put an X here. So if we had X, it's a lot of fractions. So what it would have given you here is what it is in terms of X. So this is 337 plus, and this would have been EG here.
Is that with the first one?
Yeah.
Oh, okay.
30% plus EG is equal to 490.
Yeah, it turned out to be a lot prettier than this, but this is how you would have done it in the calculator.
So you didn't have to do all the determinant stuff?
No.
And all that?
Oh,
Yeah.
I'm so sorry. I'm so sorry.
Yeah, I don't think I got it right either. But yeah, I tried to do all the determinants and everything.
I wish you could ask me that. I'm sorry. Okay.
I was gonna ask you about it after the review, but can we expect to see, we wouldn't expect to see anything like that. Or would we? I guess if you know the matrix way to do it, then it's probably pretty fair.
It's, like I said, it shouldn't take much longer than it would normally. And that's why the CAS is great to have. This is something that the CAS can do that the other one can't. Okay. Do we want to do any other MAME stuff? Yes.
Does it matter if it's a decimal or exact?
Wait, what did the question even ask?
Ooh, such a good question. This did say solve the MAME for the mesh currents. So perfectly great question though. This is going to be our correct answer. And these are all in milli, right? So that's 182 milliamps. Yes, yes.
Does it matter? Write down.
Oh, yeah.
Like, cause then if all those three are correct.
By and large, decimals. I prefer decimals. If they're like, occasionally Russell might write it in fractions for some reason unbeknownst to me. But it's a lot easier to figure out what his fraction answers are in decimal than it is to figure out what your decimal answer is in fractions. So decimal split. And like I said, if you had this, right, it gives fractions, way to get decimal, control, enter. That's all you gotta do. What else we got?
Is there a quick way to swap that back to bracket?
Just do it.
Okay.
What if I keep my calculator in engineering?
Menu, second, and then.
Yeah, so there is a way to approximate to fraction,
Okay.
but I don't, yeah. I didn't think that was gonna be very happy with me. Yes. Who had a question? Someone have a question? Did you have a question? Okay, cool. This is still an engineering format. If you want to, you can also go to the document settings here. If you want to just change it to exact, then it'll always give you
And
fraction.
then just recalculate.
Yeah.
Okay.
And remember, if you want to go back to something you had, arrow up, enter. And then you can do the fraction. Do you have any other calculator questions? I am an absolute nerd for this calculator. It is one of the coolest pieces of technology. It has a bunch of like
What other type of main questions could you ask?
MAME question. It's a good one. I don't. Yes.
It's okay, you can give us spoilers.
So I can. I wish I had. Does anybody have? I'm sure you all turned it in. Hope you all turned it in. The homework.
I can just pull up the PDF.
Like the latest.
Do you have like the first question on the homework on paper by chance?
Yeah.
Do you actually? That would be great. Because I was gonna work through the weird EG. It's oh no, I meant the second. Wow. Perfect. So I'm gonna cover up the solved bits, but this VG, I know a large majority of you came and asked me questions, but of the people who didn't, how many of this threw you for a loop? Yeah, it's funky. So there's writing here. Do you mind if I erase the pencil on here? Okay. You are a trooper. Thank you so much. So this VG, what this is, it's the same as what it was here is it's just specifying a voltage that's in the circuit. That's what this VG is. And that's important. This V2, this VG, that is not a source. That is not providing anything to the circuit. You're not going to put that in your voltage rises or equation. That is just saying, take a multimeter, take a measurement thing, and what is the voltage at this point? So what this is saying is what is the voltage from this positive to this negative? That is what this is saying. So to do that, how would a multimeter do it? Yes. Stick it. It would try to find a path from this positive terminal to that negative terminal. So what we can do is we can just draw this path. Right? So it's this way, comes down, and comes up to the negative. All that this is going to mean, and whenever we find voltages over things, wire does not have a voltage drop in this class. So the voltage from here to here is the sum of the voltages on that path. So it is just saying it's the sum of the voltage over R3 plus the voltage over R2. And so all we need to do is find the voltage drops for those two things. So the other important thing is this plus and minus. We have to preserve that. So as it goes along this path, we know that this is plus, which means that it's going to be a drop here. So it's going to be plus minus here, right? Plus minus. And then over here, it needs to stay the same direction. So it's going to stay plus minus. So it preserves this plus minus, right? Sweet. From here, we're going to write in terms of our mesh currents. I am 1, 2, 3, and 4. How can we write this voltage? Negative IM2, because remember, this IM2 is going this way, which this has plus minus like that.
And you said because we're following it back down, that's why.
Because we want this, we want positive, negative here. This is going the opposite direction. So it's going to be negative IM2 R3. Now let's do the other one. So what's the voltage over this one? Exactly. Because it is going that way. So this IM1 is saying that it's plus and minus here, and that is the opposite direction of what we need. So this it's going to be minus IM1 R2. So that is what our VG is going to be. So it did not include this source. But if it did, if it was from here to there instead of there, all we would do is just add that source. So then it would just be plus 10 VG, which would be terrible because it has the same variable in the equation. So that would never happen. But if it was just like a 10-volt source, it would just be plus 10. VG is equal to that plus 10. So that is, I know that is probably what tripped everybody up. This was the hardest question on the problem set. But just gotta make your brain think a little differently. That's what a lot of circuits is.
Just explain again how do you bring the VG?
So we are looking for the voltage difference from this positive to this negative, right? So we are going to look for the path from this positive to this negative, right? So we're going to take this path down, over, up to the negative. We want the voltage, the sum of the voltage drops. So it encounters two resistors on the path, right? So we need to add up the resistor, the voltage drop over this resistor, and then this resistor. And because this is MAME, we're going to write them in terms of our mesh currents. So to do that, we look up for this drop. So we know positive, negative here. This current is going the opposite direction. This IM2 has the plus and minus like that. Are these plus and minuses going in the same way? Okay, so it's going to be negative IM2, right? Times R3. Because we want voltage and mesh currents are not voltage. So we need to use our Ohm's law. Right? At the end, just check your units, right? If you are trying to figure out if you need to use an equation or not. You have current and you're trying to get voltage, then you should probably multiply it by the resistor. And then on this side, same thing. Are you good with the plus and minuses? Okay, so we follow again, plus minus here. This mesh current is the only current flowing through this resistor. This mesh current is saying that plus minus is open that way. So it's minus. So it's going to be IM2 R3 minus IM1 R2. So that's what VG is equal to. Cool. Sweet.
If we remove on plastic, reacting.
I was saying hypothetically. What if our VG, it was from here to here? Like hypothetically, if VG was from this point to this point instead of from this point to that point, we would have to add in this voltage source. That's all I was saying. That was just a hypothetical. That's not what it actually is. Okay. Got more questions, comments, concerns?
Do you recommend that we cast this one specifically?
Yeah. I think if you understand that one, you're going to be pretty good on main. Yeah. And while we're at it, now that I have this printed out problem set, thank you very much again. We can do this current divider problem because this one isn't too bad. We can circle back. So I'm just going to solve this up.
Find out everything. Figure out why it's
I thank you for it. So we have current source and we have a bunch of resistors in parallel. To do the current divider, we need them to all be together. We need a total resistance on the branch. So we need the resistance from this point to this point all added together. To do that, here we need to first combine in series and then combine in parallel. So let's go ahead and write out what that's going to be. So it's going to be, what is that? 4. Now help me out with the values.
So 4422.
4422. Beautiful. So from here, we just do our current divider. So find Ix, what we're looking for. It's going to be I total, which this is our I total, times 1 over R X. And a useful thing, if you have a bunch of them in parallel, your denominator is not going to change, right? It is going to be the same thing. So all you need to do is just go in and change whatever you're looking for. So we can just do this. So we want 12 times big fraction. So we'll do first 1 over 4. And then 1 over 4 plus 1 over 4. 2 over 2 over 2. That's 2. So I just did, these are what we got for our branches. So what I did is I did 1 over 4 because we're looking for this current. I didn't say that. For the first current, for I1, it's going to be this 4 divided by the total. So what's the current here going to be? Yep, perfect. 2. And then if we wanted to change it to the other one, all we do is we go to 2. We just change the numerator. The denominator is the same. Yes. This is the resistor that we're looking for. So for the 2s, it's 1 over 2 divided by 1 over 4, 1 over 4. 2. So 1, 2, 3, 4 is going to be 2, 2, 4, 4. Now, what is I5, 6, and 7 going to be? How do we find those?
Because I'm just going back.
Yep. Yes, so 5, 6, 7. Are we going to use this 12 milliamps? So we are now looking at 2 different problems. We're looking at a current divider between I3, and the current's going to divide over this resistor and this resistor. So I5, we're going to take this current and do another current divider.
4 milliamps is just the VYT.
Exactly. So now what it's going to be is I5 4 times 1 over 3, 3 plus 1 over 6 is equal to, do you know off the top of your head? No. 8 over 3? That sounds right. And then I6 going to be. So total is 4, right? our total is 4. And then we have 3 branches. It's going to be, so it's 1/6 divided by 1/6 plus 1/4 plus 1/12. So it needs to be the sum of these two. It can't just be 4. It needs to be both of them. That's going to equal like 1.3 or something. Sorry. 3, and then 7 is the exact same, except it's going to be on the top 1/12. And then the same thing. Right? Sweet. So that's how you do, if you see a current divider within a current divider, just make sure you use the new total. Sweet. How we doing? Do we got anything else? We got more questions?
I have a calculator question.
Yes.
How do you get the big fraction to show up?
Yes. So you're gonna do the dividing symbol, right? And then if you want another fraction on the top, you're gonna do another fraction there. So I just So I just did 1 and then I did another big fraction. And so now this is the top fraction. So then 2. And then over here I want 1 divided
You're
by
getting
2.
control of divide.
Yes.
Do that. Okay.
Yes.
I don't know. I'm getting really tired of keeping track of parentheses.
You're good.
Yeah.
Oh yeah, parentheses are terrible.
That's good for the pocket.
Yes. Yes.
Just on the last one, you do the same thing, it's gonna be 1 total. Well, these
12?
That's to calculate, I said.
Yes. So I did 1/12 because that's the total resistance, right? Through I7.
So the placement of I7 doesn't say anything. It's just the current in that branch. So it's not like the current of the 4 ohm resistor.
Correct.
Of that. Okay.
Yeah, because are those going to be any different? The current through the 4 ohm and the current through the 8 ohm?
Oh, yeah. Current coming out of the 4 ohm might be different after going through the 8 ohm.
A current through a series branch is always.
Yeah, that's true. It's
So I wrote ... here just because it's the exact same as that. So it's just 1/6, 1/4, 1/12. Because those are the same thing. They're coming from I4. So the denominator is the exact same. And these are, again, useful tricks because the test goes fast. So, yes. These are going to be the 4 questions. They're different. So like some of the resistor combinations are super easy and then some are more like this one. And so like the final last semester, the MAME was the easiest question I've ever seen in my life. It good stuff. It was like everything worked out so that almost everything canceled. And the answer was just 1, 2, 3, 4 or something. It was crazy. Yeah. Yes.
How would you solve it?
Yes.
How do you solve on? Yeah, if you have 100 in each of those.
Okay. Yeah, that is an excellent question. If we had resistors here, we would have to condense it down and then expand it back out.
You keep it or give it to me later.
Sounds good. Thanks, man. You too. Yes. I mean, it's not like I require you to figure out how to use this calculator. The meshes just are a lot easier.
Yeah, you know, for like dividing.
Yeah, no, of course, of course. If you have resistors here, so redraw another circuit, just so that so for this, right? So this current here isn't directly connected. So it's not going to be a direct current divider. So what we're going to have to do for this one is condense it down to where it is just a current, and then it just where it divides over two things. So we're going to condense this down so that it becomes a current and then two in parallel. And then from there, we're going to figure out this current. So we find out what this current is, right? Which is the same as this current. And then from there, we do another division. So we take this is like I2, it's I2. And then we use this I2, one second. We use this I2 and then expand it back out and do the current divider over the next two. Does that make sense? So you condense it all down so that it looks like this. Then you do the divider, and then you do the same thing where you use the new current because you did the current over the second resistor. You would then do the new current as the new total current.
So if we have I2 and then we're just left with trying to figure out what the current going to the next one would be, so you just add the two at the very end, compare in series and just beat with them.
Exactly. Or do another current divider.
So the resistors on the top for that, would you ignore those resistors previously?
Which resistors? This one or all of them?
The ones on top of.
So if you have them on top, you need to condense it down. So you would need to take this and go here. And this resistor is an equivalent. So you have to combine these in parallel and then put them in series. Yes. And that's how much current is going to be going through that branch. And then once you figure out what current is going through here, then you're going to do another divider. So you're going to take these two in series and do a current divider between these two and this one. Cool.
Then like the order you solve.
They should both be in and out. You should, yes, I see what you're saying. You're going to condense it first and then do it step by step and expand them both out. Right? Cool. Got any more questions?
I think I'm thinking about source dominance.
The source transformation?
Yeah.
Yeah. Yes.
So the 34 and 66, you just added 16 to 34 and subtracted.
Yes.
Oh,
Yeah. And they're all going, these two are going the same direction. So it's 34 plus 16 minus 66. Because it's going in the opposite direction. Cool. Yes. You're good. You're good. So I hope that's okay. It'll be immediately available on the HKN Teams. I'll try to get someone to upload it to the YouTube. But I can send out the link for the Teams pretty much right after this. Yep. As long as you put their like order like on top or bottom, no. As long as it's in series with the voltage source and in parallel with the current source. Mhm.
You have to be. Do you have to be in the HKN Teams to see the link? For the link to work?
I think it'll just take you to the Teams.
Okay.
You can also just search on Teams HKN virtual office, I'm pretty sure. But I'll also just send a thing. Some old good stuff on there.
And you said there was more reviews stuff on the right. Yeah.
Mhm.
Yeah. We use like internet, right? But why we use that? But how do you know that? Like, that's not that we have right way to solve this circuit to solve.
Why? How do we know what?
How do we know that we have to do measurements?
It'll tell you. It'll tell you. It'll say in the question.
No, I'm not talking about that. Like, who invented that? We have to do
Russell.
matrices like that, and it will be that.
Russell. He created name and name.
He has his own documents over it.
Mhm. Yeah.
Yeah, that's interesting.
Mhm. That man is smart.
Wait. Is it recognized nationally? Is it recognized nationally? Really?
Yeah.
It means that does
You should go ask him about that.
Sounds like a.
does he use the same method?
He like someone tried to steal it from him. Someone tried to steal the patent from him, and he doesn't have the original papers anymore. So he can't go like get the patent for it. He's upset about it. In textbooks, they teach something called by inspection, which is similar to how they solve this. It's the exact same of doing this passive matrix. The difference between what textbooks teach and what we teach is the dependent side. So the textbook that I use isn't the textbook that he gives for the class. I just have a textbook that I have that I like. And it says in there like the only way that you can do by inspection is if it's purely independent matrix, like a purely independent circuit. But being able to do this with the dependent sources is really cool.
When you say independent circuit, you just mean one independent source. That's it.
No, it can be a bunch of like independent sources, so a bunch of batteries, just no dependent things. And then he is gonna teach Thevenins and Nortons. I talked to him about that today. And you're gonna use Thevenins and Norton. You're gonna use Mayman name for Thevenins and Nortons, which is really, really cool. And he'll either do the pentagram problem or I'll do the pentagram problem, or he'll give it in your homework or something. And it's my favorite problem.
There's a pentagram problem. And materials.
It's great.
Yeah.
Are you able to just send it?
Yeah, I'll send it in Canvas. Don't worry, I'll send it. If we got any more questions, I'll stop the recording if I think we're good. Cool.
I feel like you're